Hello, everyone. Today we're going to be talking about conjugated systems, Dienes, and Diels-Alder. And I'm going to move this out of the way. Excuse me. Oh my God. This freaking thing always relocates itself at the most inconvenient moments. All right, we're going to move that right there. All right, cool. So just as a reminder, the conjugated systems are basically involve an atom that has a p orbital adjacent to a pi bond, right? So the p orbital is going to be located right here. P orbital. We got a pi bond right here. Pi bond right here. Actually, wait, I should probably move these this. Yeah. So you're going to be doing some reactions with conjugated systems, and there's some associated trivia you kind of need to know with it. But essentially, the way that I personally kind of visually identified a conjugated system, right, was that if you have a series of pi bonds, right, that are capable of doing resonance with each other, right, they're within resonance range, right? I would call it conjugated. Now, this may not be exactly academically sound, right? But this works for the purposes of the class. So, for example, right, I can prove it to you. This system right here, right? This thing 1,3 butadiene, right? 1,3 butadiene, right, is capable of doing resonance. Let me move this over here. Anyways, I wrote that in my way. Right? I can do this. I can do this. We end up with this, right? Let's charge right here. Yep, and I can move this back. We're all within resonance range of each other. Yep, and I can move it through the other way as well. And so, example over here, right, is that this over here isn't a fully conjugated system. Why? Well, because I can't really move this pi bond onto here, right? Because it would violate the octet rule here. Violates octet rule. If you're confused, go see my video about resonance. You should practice this. It's going to be the death of you if you aren't able to comprehend resonance. So that violates the octet rules. This is not fully conjugated. Not really a conjugated system. Okay. And there's also, right, some allylic systems, right? You can also see this sometimes too, right? Where we have those those lovely, lovely radicals, right? So because we're working with only like, one electron moving around at a time, we have to use those lovely half arrows, right? This is a fully conjugated system too, over here as well. And I can move it the opposite of the direction as well. So we're going to be doing some reactions with these conjugated systems. First and foremost, right, starting off with dienes, right? So dienes, right, the 1,3 beta right, is just one of the it's mainly probably one the default template for the type of reactions we're going to be doing. You can often find them in trans conformations, right? So it's going to be like this. Why? Because if you have it in the cis conformation, right, it's unstable, right? So yeah, and from here, right, we're going to go on into some of the reactions that we can do here. And so I'm going to move down over to here, right? So this is one of the reactions that we're going to be doing here, right? We're basically just going to be, this should look very, very similar to 8A, where you basically have a double bonds, right? And you have, I kind of forgot the name of this, the name of this reaction. I believe it was halogenation. I could be wrong, right? Where you put a halogen onto something. So, right, hopefully you guys kind of roughly remember how to do this type of reaction, right? We're going to start off, right, with this double bond coming here and attacking, right, being a nucleophile. It's electron rich, so that H is very electron poor, so it's going to facilitate this attack there, right? And then you are going to, I should probably do this down here. You are going to get this, right? You're going to get this. This H is going to go onto here. Now, you may be asking, why specifically does that H go onto there, right? Well, by putting that H onto the far end of this 1,3 beta diene, right, what's going to happen is that you're going to open up a possibility for a plus charge to end up here, right? Or open up a possibility for a plus charge to end up here. Now, with that plus charge, right, there can be resonance stabilization, right? Resonance stabilization, right? Alternatively, right, if we went in this direction, right, alternative, if we ended up doing something like this, let's see here. And the plus drive ended up right here, right? No resonance is possible, and it's less stable. And ideally, right, it seems to me, right, from my personal experience, that molecules or just things that happen in organic chemistry, right, will always tend to favor the outcomes that leave it more stable, right? Atoms, molecules, compounds always love stability. They seek to be stable, right? So this side doesn't happen, not likely, right? And so from here, right, you can get two possible outcomes here, right? So first possible outcome, right, is that outcome one, you have two products here. Outcome one is that from here, the CL just kind of comes in and attacks and does its thing, right? It'll just attach itself onto that plus charge right there, right? You have negatively charged CL here, attack right there. You end up with this. Okay? You end up with this product. Now the other outcome, right? Outcome two is that resonance stabilization will kick in. When that happens, right? Some resonance over here, right? And then you're going to get this plus charge is going to end up over here, right? And then from there, right, your CL moves in and attacks. And then you're going to end up with this. So we now have, this is really ugly. I'm gonna reject this. So we now have two products, two possible products here, right? Now, in this scenario, right, this product over here, right, is faster, right? This product forms faster, but it's more unstable. This is called the kinetic product. Okay? This guy over here, right, is, ooh, I'm gonna give myself a little bit more space here, called the thermodynamic product. Oopsies. Right? It's slower, right, but more stable. Slower to form, but more stable. Now, the real question here is going to be which one of these is going to be the major product, which one's going to be the minor product in this scenario, right? Well, it depends on your starting conditions. If you look up, right, well, there's a very, very easy way to distinguish it, right? But this happens in 25 C, roughly room temperature, right? And so in room temperature conditions, right, the kinetic product is going to be, right, major in room temperature conditions, right? And this is going to be the minor product over here. However, if you switch the conditions, right? If you heated this bad boy up, right? If you instead of 25 C, there was heat underneath it, right? And you left it in there for a long time, and the thermodynamic product is going to be, I'm going to move this practice problem down there. I always, always, always underestimate the amount of space I need, right? However, right, if you had a scenario like this, let's say, for example, right? HCl, heat and then time, or just heat, right? Then the scenario is going to be the opposite, right? Thermodynamic product is going to be favored. And so from here, we're going to go do a quick practice problem here, right? And we're going to go ahead and draw the two possible products out of this and determine which one's major and which one's minor. If you guys want to pause the video and try it on your own, I do welcome you to do so. Alrighty, cool. So an HCl here, right? That's going to come into here. It's going to pop up onto here. We're going to end up with this. Right? H right here. It's right here, right? We put the H right there because we want to have the possibility of resonance stabilization. It's going to go tack into here, right? We could also have the scenario, right, of this. Oops. H right here, right? This right here, plus charge right here. We do some resonance. Plus charge right here. CO moves in. Yep. This is the kinetic product. This is the thermodynamic. And if you look at the starting conditions, right, we didn't specify that it was there was any heat underneath it, right? So if it's no heat, right, just assume it's room temperature. So this is going to be the major product. This is going to be minor. Okay, cool. So that's basically all I have to say about the dienes and the kinetic versus thermodynamic. We're going to move on to Diels-Alder. So the people who discovered Diels-Alder was a professor and a student, and they won the Nobel Prize. So, if you ever want to win a Nobel Prize for chemistry, I guess they just create a really interesting reaction. So, yeah, I'm not too entirely sure about the industrial applications of Diels-Alder. I probably should have Googled that before I started yapping about Nobel Prizes, but whatever, it's fine. So, so Diels-Alder is right. There's two elements to, or two parts to a Diels-Alder reaction, right? You have a conjugated diene. Oops, that's an M. You have a conjugated diene. I'm going to move this little down here as well. Conjugated diene. And you have a dienophile, right? Now, generally, right, you want your conjugated diene, right, to be E rich, electron rich. And you want your dienophile to be relatively, compared to the conjugated diene, to be E poor, electron poor. And so you guys have probably had some experience in lab with Diels-Alder reactions. But we're gonna go ahead and kind of redo the mechanism here. So it's pretty simple, I would say, right? It's all kind of like just one giant mechanism here. Do. This goes on to here, right? I probably shouldn't use the same colors. I might actually confuse people. Purple, right? And then orange is gonna go onto here. And so we're gonna do this in a way for you to kind of visualize, right, where everything's going. The way I kind of imagine this type of reaction going is like it's like if you had a pocket knife, right, and you're flicking open the double bonds, right? That's how I imagine it in my head. Or if you like have one of those camping chairs, right, the ones that like fold inwards, right, the ones that people use to sit around a fire, right? Um, those are also really good analogies too, right? So you're flicking it open, you're forming a ring. Hmm. So yep, that's there. Yep, that's there. I'm gonna put this bad boy right here, right? This is called a cycloaddict, or you can also say Diels-Alder uh, addict. Yeah, funny little names. So yeah, generally, right, Diels-Alder reactions take a really long time to do, and I forgot to mention this too. But yeah, heat this bad boy up to 200 C. Yikes, that is hot, right? And obviously, I guess chemists are lazy, I guess, like why would we want to like sit and wait a long time and basically cook our reactions for up to 200 C, right? Nobody wants to do that. So there's a couple ways you can make Diels-Alder reactions go a little faster, right? And the first thing is with electron withdrawing groups and electron donating groups. And so, kind of quick summary of both, right? Electron withdrawing groups, right, are basically just kind of any group that's via resonance, right? You withdraw electrons, right? So you have something along the lines of this, right? This is an example of a electron withdrawing group, right? Because it withdraws, it's like a vacuum, right? Sucks up electrons, sucks up electrons all the way up here, right? And so these electron withdrawing groups, right? If you add them onto the dienophile, right? So if you had a dienophile that looks something like this, right? Right? It would generally speed up the reaction. So to put these guys, puts EDGs, or EWGs onto dienophile, right? On the opposite case, right? Electron donating groups, right, would be basically just kind of any group that kind of donates electrons. How do I wanna do this? Oh yeah, we'll do this. Right? So we had something on the lines of like an oxygen kind of just chilling on its own, right? And resonance-wise, they donate it down. They push electrons down onto this. Okay, right? Now, if you put these bad boys, right, onto the dienes, right, generally that'll also help speed up the reaction too. Oops, let me just give another color for this. Put EDGs onto diene. Yep. So if you put the EDGs onto dienes, right, and put EWGs, right, onto dienophiles, right, then ideally, right, you can kind of help speed up the reaction. So if you have both, great for you. But if you have to choose only one, I mean, choose either one, that's fine. And so, yeah, and I probably should have also written this out too. EWG, electron withdrawing groups. It's withdrawing, right? And blue's going to be electron donating groups. Right. Now, I think the real meat and challenge of Diels-Alder reactions is trying to figure out what the substituents will look like, right? Because if you throw on EWGs and EDGs, right, you end up with substituents. And fortunately, Diels-Alder reactions are very, very, you got to be very specific about their stereochemistry. So let's kind of go over an example of this right here, right? So so I have two EWGs here. And so let's kind of quickly kind of do the reaction here, right? And let's kind of figure out, right, and give you a snapshot of what the reactants would look like. Sorry, the substituents would look like. If you guys want to pause the video and try to attempt it yourself, right, I'd welcome you to do so. Mhm. All right, I'm going to go ahead. I'm going to choose a different color for this. Okay, great. So we're going to end up with this right here, right? And purple. Uh-huh. Light green, lime green. And this is going to be right here. All right, cool. So make sure you have the base structure of it good. And so basically, right, if it's pointing this way, right, if you like our red here, right, if it's pointing that way, then it's going to be a dash. If it's pointing the opposite direction, right, if it's pointing this way, right, it's going to be a wedge. Mhm. Yep. There's also some other scenarios too, right? So this is covers, right, putting EWGs, right, on the dienophile, right? The good news for you, right, is that hypothetically, right, if I, let's say for example, if I drew on a, let's see what color I want to use here. Yeah, if I drew on an EDG here, right? Oxygen, right? Oxygen, OH, right? You don't have to worry about you really don't have to worry about the stereochemistry of the of any EDGs. You just throw them onto here, right? This is what that looks like. Mhm. Yep. Alrighty, so let's do some practice problems over here, right? I got some somewhat challenging ones here, so we're gonna go ahead and attempt those. And so yeah, we'll go ahead and I encourage you to kind of pause the video, right? And you guys can kind of figure that out by now. All right, let's go ahead. Alrighty, cool. So let's go ahead and let's kind of go ahead and get started. So this guy right here, right? This will tack onto here. This will tack onto here. This will tack onto here. So you're going to end up with this cycloadduct. This one's a little different, right? Because, well, you have a triple bond over here, right? But don't worry. That in the other scenarios, right, where you had a double bond that kind of just disappeared on this end, right? Triple bond just means that you have another double bond there. Nothing too crazy. All right, cool. On top of that, too, you could also use an allene, right, in your reaction, right? I'm going totally out of order here, but who cares? Whatever. Right? It's going to go onto here. This is going to go onto here. And this is going to go onto here. I'm probably a little more specific about the arrows that I use here. Anyways. And then, right, if you notice, right, with double bonds, right, there's really no stereochemistry there because, well, they're flat, right? So if it's flat, there's no stereochemistry. What's the point, right? Over here, right, we have furan. You probably use that in your lab, right? And you might be a little confused about how exactly we're going to go about doing this, right? But I'm going to go ahead. I'm going to kind of highlight this in different colors for you so you can kind of see visually how this is going to resolve itself. Red, sorry, blue, red's going to come over here, and then this bad boy's going to attack in this direction. Alrighty, so all right, that substituent over there is hanging that direction, so I get to do this, right? And so the only weird thing about this, right, is that so you guys see this oxygen in the middle, right? This little ether, right? I would imagine, right? Just imagine that you're taking that ether. It's like you're pulling a fire alarm, right? Where you're taking this, right, and then you're pulling it back this way, so that's like this, right? Just, it's you're pulling it back that way. Like you're cranking a fire alarm. Yep. So you can't really see this right now, right? But this is basically uh like a furan being pulled. You're pulling a fire alarm, right? And it's basically now standing upwards. I should probably also do the stereochemistry. It's standing upwards, pointing out at you, right? I can't really. Let's see. Can I draw it? I wonder if I can draw it. We'll see. It would basically look something along the lines of this, right? This is looking at it from like an elevated perspective. Hopefully that helps. Right? Goes right here. Orange is right here. Yep. It's a very, very odd, weird scenario, right? But this is basically what it looks like. Damn, that actually turned out a lot better than I thought. Alternate view. Also, I have no clue if this is. I don't know. There might be some formal way to denote that you're like changing your perspective. This is how I do it usually. No one's really yelled at me about it yet. So, anyways, yeah. And then over here we have this right here, right? Got a ketone. Got some funky things going on here. Oopsies. Ooh, I'm gonna have to. Ugh. Fun fact: you can make your arrows as wild and wacky and as crazy as you want. as long as they're pointing in the right spot. So hypothetically, if you really, really wanted to mess up a TA's day, you can literally like draw an arrow like this. I don't recommend you do that, but also if you do it, don't tell them I said anything about that. They'll hate me forever. So anyways, then you'll have a cycle addict like so. Mhm. Alrighty, let me make this a little bigger. It's going to be here, and you're going to be that boy right here. Let me separate this so it doesn't look weird. All right, cool. CH3. Okay, cool. So yeah, those are basically just want to triple check and make sure I did everything correctly and make sure I didn't screw up. Anyways, so yeah, that was all of the stuff related to conjugated systems. If you have any other questions, please feel free to find me. If not, then well, good luck studying. I'll see you guys around.